Imagine trying to build something incredibly small, smaller than a speck of dust, and not only that, but shaping it really precisely, say, into a perfect little triangle or a tiny rod using two different metals mixed together. Sounds, well, almost impossible, right?
It really does, and that's the kind of challenge researchers face when they're trying to create these complex metal nanoparticles, with specific shapes for some cutting-edge technologies.
Yeah, it's a fundamental thing in nanotechnology, isn't it? Being able to control materials at that tiny scale.
Absolutely.
Yeah.
Because their properties, how they behave,
Yeah.
are so dependent on their size and their exact form. It's key for, well, all sorts of scientific and engineering progress.
Okay, so this scientific paper we're looking at today, it's titled Morphology Preserved Alloying in Anisotropic Gold Nanoparticles. Using atomically precise nanoclusters, it actually describes a new and honestly surprisingly simple way to do this. They've managed to create gold-copper alloy nanoparticles, those little triangles, rods, cubes I mentioned, and here's the kicker. They did it while keeping the original shapes perfectly intact.
And what's really interesting here, I think, is how they did it. It's not the usual high-energy stuff, extreme heat or lasers to force the metals together. No, they're using these incredibly well-defined structures called nanoclusters, atomically precise building blocks, essentially.
Exactly. So that's the mission for this deep dive, right? We want to really dig into this new technique, understand how it works, and, crucially, why preserving the shape so perfectly while alloying is such a big deal, such a leap forward for nanotech.
Sounds good.
Okay, let's get into it then. Why has it been so hard, traditionally, to make these alloy nanoparticles that aren't just tiny spheres?
Well, the main difficulty really is controlling the very first steps, what we call nucleation and growth, for two different metals at the same time.
Okay.
See, each metal kind of has its own way it likes to stack its atoms, its crystal structure, and its own reaction speed. Trying to mix them, well, they might not want to combine uniformly. You could easily end up with something messy, sort of blob-like, instead of that perfect triangle or cube you were aiming for.
Right, like trying to get oil and water to mix perfectly, but on a scale you literally can't see.
That's actually a pretty good analogy. Yeah. Traditional methods often use high temperatures, right? Which gives lots of energy, sure, but it makes it incredibly hard to keep those delicate nanoscale shapes stable.
They just melt or deform?
Pretty much.
Yeah.
Or other methods, maybe using lasers or specific chemicals. They might work for some shapes, but you often can't independently control both the final shape and the exact composition, the ratio of the metals.
Ah, okay. So you might get the perfect shape, but the gold-copper mix isn't quite right for what you need it for, or the other way around. The paper really flags this as a key problem needing that separate control.
Exactly.
So how does this new strategy, the one using these atomically precise nanoclusters, get around that? What are these nanoclusters actually doing?
So the core idea is to use these specific copper nanoclusters. The paper calls them Cu18, DPPE, 6H162, plus CoA, or just CO18 for short.
Cu18, got it.
As a sort of precursor material. They use it to essentially infuse copper atoms into gold nanoparticles that already exist in the desired shapes.
Ah, so you're not building from scratch. You're taking a perfectly formed gold shape and gently adding copper into it.
Precisely. Think of it like carefully adding a new spice into a dish that's already perfectly plated without messing up the presentation at all.
Okay, I like that. So they started with gold shapes, like those triangles you mentioned, N and T's.
Yep, gold nanotriangles, N and T's. They use those as their initial model system. And it makes sense because, as the paper notes, the sharp points and edges on those triangles are really sensitive.
Right, and they'd show damage easily.
Exactly. So if their method could add copper without blunting those corners or changing the overall triangle shape, that would be pretty strong proof it's a controlled shape-preserving process.
And that shape matters, right? It's not just about looking pretty.
Oh, absolutely not. Especially for things like catalysis. Those sharp corners, specific crystal faces, those are often the most reactive spots. If you mess up the shape while alloying, you could kill the catalytic activity. So preserving the shape means you can potentially design catalysts with really precise performance.
Okay, so walk us through it. What actually happens when they mix these gold nanotriangles, the NNTs, with the C18 nanoclusters? What are the steps?
It's surprisingly straightforward. They start with a solution of these really uniform gold nanotriangles, about 75 nanometers on each side, in a solvent, DMF.
Yeah.
Then they just add the C18 nanoclusters to that solution, and they stir it moderately at room temperature.
Room temperature, seriously. That sounds incredibly gentle compared to the high heat and lasers.
It is. Very mild conditions, and they see a change almost right away.
What's the first sign?
They observed a red shift in the UVV's absorption spectrum. Basically, nanoparticles absorb light in specific ways, creating a color spectrum. When the composition changes, how they interact with light changes too.
So the color shifts.
Exactly. The pattern shifts towards the red end of the spectrum. That's a really strong early clue that the gold and copper are mixing, forming a new material with different electronic properties. It's like a little signal saying, hey, something new is happening here.
Okay, so the light tells them these aren't just gold anymore. But how do they know the triangles are still, perfectly triangular?
Well, that's where the high-powered microscopes come in. They use transmission electron microscopy, TEM,
Right.
to get actual images of the nanoparticles after the reaction. And those images, they clearly show the nanotriangle shape was kept. And not just that, they measured lots of them and found the average edge length, the size distribution, was pretty much identical to the starting gold ones.
Wow, okay. That visual evidence is pretty compelling. But hang on, just because they look like triangles, does that definitely mean the gold and copper are mixed evenly inside? Couldn't the copper just be like a thin coating on the outside?
Excellent question. And that's absolutely critical. So they used even more advanced techniques to look inside the triangles. One is called Stemmen scanning transmission electron microscopy with energy dispersive X-ray spectroscopy.
That sounds complicated.
It is powerful. It lets them not only see individual nanoparticles really clearly, but also map out where the different elements are within each particle, like getting a detailed chemical map of every single tiny triangle.
So they can see where the gold is and where the copper is?
Precisely. And what they found was a completely homogeneous distribution. Gold and copper mixed evenly throughout the entire volume. No sign of a copper shell around a gold core or anything like that, just a uniform blend.
Okay, that's convincing.
And they backed that up with another technique, ICP-MS, which measures the overall composition very accurately. That confirmed the average ratio was about 5.7 parts gold to 1 part copper in these final ochencetes.
So multiple different methods all saying the same thing. Uniform alloy, shape preserved. What about the actual crystal structure? Did putting copper into the gold lattice change how the atoms are arranged?
Good point. They looked at that using powder X-ray diffraction, or PXRD. This technique looks at how X-rays bounce off the atomic layers inside the crystal.
Okay.
They saw a pattern characteristic of what's called a face-centered cubic, or FCC, structure, which is what both pure gold and pure copper have. But importantly, they saw a slight shift in the position of the pattern's peaks.
Shift. What does that mean?
Think of the atoms in the crystal like a grid. Copper atoms are a bit smaller than gold atoms. When you mix the smaller copper atoms into the gold grid, the average spacing between atoms shrinks slightly.
Like replacing some big marbles with smaller ones in a box.
Exactly. That change in spacing causes the X-rays to bounce off at slightly different angles, shifting the peaks in the PXRD pattern. This shift confirmed that copper was indeed incorporated into the gold lattice, shrinking it slightly and proving it formed a true alloy.
And this wasn't just on the surface.
No, the calculations they did based on that shift suggested a uniform alloy composition throughout the whole nanoparticle, roughly 88% gold, 12% copper, which again rules out the idea of just a copper coating.
Makes sense.
And one other detail from the PXRD, they didn't see something called a superlattice peak. The absence of that peak suggests the gold and copper atoms are mixed randomly within the FCC structure, rather than arranging themselves in a highly ordered alternating pattern.
Okay, so it's a well-mixed random alloy, keeping its perfect triangular shape. That's impressive. But can they actually control how much copper goes in? Because 12% might be good for one thing, but maybe you need 30% for another application.
Absolutely crucial point. And yes, that's another major win for this method. They found they could control the copper content just by changing how much of the C18 nanocluster solution they added at the start.
Seriously, it's that simple, like adjusting a recipe.
Pretty much. They saw a direct, almost linear relationship. Add more CU18 solution, you get a higher percentage of copper in the final alloy triangles. At least up to about 60% copper, they showed this nice control.
Wow, that level of compositional tuning is huge, isn't it?
It's incredibly valuable because even small tweaks in the metal ratio can drastically change the nanoparticle's properties, how it interacts with light, how it performs as a catalyst. This gives you real power to fine-tune them.
Now, you mentioned copper. Isn't copper notorious for, well, tarnishing? Oxidizing? Does that happen here? Because a nanoparticle covered in copper oxide might not be very useful.
That's a very practical concern, and they definitely looked into it. First, the XRD data we talked about, it showed no signs of copper oxide peaks.
Okay, good start.
And then they used surface-sensitive techniques, XPS and auger spectroscopy, which are really good at telling you the chemical state of atoms right at the surface. And these confirmed the copper within the Alkantes was predominantly in its metallic form, CO0, not oxidized.
So the gold is kind of protecting the copper within the alloy.
That seems to be the case. It suggests the alloy structure provides some stability against oxidation, which is obviously a big plus for actually using these things.
Definitely a huge plus. Okay, now this whole mechanism sounds a bit weird. You said copper is generally less noble than gold, so gold usually doesn't like to react or be displaced. How does this anti-galvanic thing work where copper seems to be kicking gold out?
Yeah, this is probably the most scientifically intriguing part. It is counterintuitive based on bulk chemistry. They actually observed gold ions, specifically Iu2, BPPE22, plus leaching out into the solution during the reaction.
Gold leaving the nanoparticle, while copper goes.
Exactly. Unexpected, right. But at the nanoscale, things can get weird. Quantum confinement effects, basically, the physics of electrons being squeezed into tiny spaces, can actually change the fundamental electrochemical potentials of metals.
So the normal rules don't quite apply.
Not strictly. These quantum effects can make reactions that seem unfavorable in bulk, like a less noble metal, copper, oxidizing a more noble one, gold, actually become possible. This anti-galvanic reduction, or AGR, has been seen before in other tiny systems.
Okay, so nanoscale weirdness allows copper to push gold out. How does it happen mechanically? What are those DPPE ligands doing?
Right, so the thinking is the initial Cu18 cluster probably breaks down slightly in the solution, forming some reactive copper complexes, maybe like CUX-DPP plus CARPEX. These complexes then interact with the gold nanotriangle surface.
And the DPPE molecules, the phosphine ligands, they're attached to the copper, right?
Yes, they act like little chemical handles. Yeah. And they seem crucial. The researchers suggest that maybe some gold atoms on the anti surface aren't perfectly covered by the original stabilizing surfactant molecules used to make the triangles.
Little gaps in the protective layer?
Potentially. These slightly exposed gold atoms might be the starting points. The DPPE ligands on the copper complex might then bridge the copper to these gold atoms, sort of lowering the energy needed for an exchange to happen.
Like a molecular facilitator?
Kind of, yeah. Facilitating the swap.
Mm-hmm.
Gold ions detach, complex with DPPE perhaps, and copper atoms take their place in the lattice.
Interesting. So what's the proposed sequence?
They suggest a four-step process. 1, the Cu18 decomposes into these reactive copper phosphine bits. 2, these bits attach to the gold surface. 3, the DPPE helps swap copper for gold, releasing gold ions. 4, the newly added copper atoms then probably wiggle their way into the core of the nanoparticle to find a more stable position, energetically speaking, while the overall shape stays put.
Wow. That's quite an intricate dance happening on such a tiny scale. Now, they didn't just stick to triangles, did they? You mentioned rods and cubes earlier. Did the method work just as well for those?
It did, and this really shows the versatility. They were in the exact same protocol, room temperature, mixing with C18, but starting with gold nanocubes, AONCBs, and gold nanorods, AONRs. And using TEM and another imaging technique, FESM, they saw the same thing. The original cube and rod shapes were beautifully preserved. They ended up with Akinades and Akinars.
No distorted cubes or bent rods?
Nope, perfect preservation. And again, EDS mapping showed the gold and copper were mixed homogeneously inside these shapes too. They got about 36% copper in the cubes and 22% in the rods in their examples.
So the method doesn't seem to care what the starting shape is.
Exactly. And that's a big deal. The paper highlights this is, as far as they know, the first method that can make gold-copper alloys at room temperature that works regardless of the starting nanoparticle shape without messing up that shape. That's a significant step up from shape-specific methods.
It really sounds much more flexible. Did they push it even further towards, say, 3 metals?
They did, as a sort of proof of concept. They took the gold-copper alloy triangles they'd already made, the Alkanentes, and then reacted those with silver nanoclusters of different type, Ag25.
Whoa! Gold, copper, and silver in a triangle.
Yep. Using STEM and EDS again, they confirmed they formed Alkantes trimetallic alloy nanotriangles with all 3 metals distributed inside.
That's amazing complexity.
It is. Now, in this specific experiment, the amount of silver that got incorporated was fairly low, less than 10%. And they didn't see a big shift in the XRD peaks like they did with copper.
So maybe the silver was more on the surface this time?
That's what it suggests. Perhaps the surface-limited doping in this case. But still, the key point is it worked. It shows you can potentially use this approach to sequentially react with one nanocluster then another, to build up even more complex multi-metal nanostructures.
It really opens the door to designing some very sophisticated materials.
Exactly. It hints at the possibility of really fine-tuning properties by combining multiple metals in these precise shapes.
This is genuinely fascinating stuff. Okay, so let's try and wrap this up. What's the main takeaway message from our deep dive into this paper?
I think the core finding is this. Researchers have found a really versatile and actually quite simple room temperature method using these precise copper nanoclusters to create gold-copper alloy nanoparticles. And critically, they can do this for various complex shapes, triangles, rods, cubes, while keeping those shapes perfectly preserved.
And the significance. Why should you care about this?
Well, it overcomes big hurdles from previous methods. The struggle to control shape during alloying, the need for harsh conditions. This new technique gives much better control over both the shape and the metal recipe, the composition.
Which is key for tailoring performance.
Absolutely. Tailoring them for specific jobs in catalysis, sensing, electronics, you name it. And the potential to extend this to 3 or more metals, that opens up a whole new design space for materials with really complex, tailored functions.
It really does seem remarkable. It makes you think, doesn't it? What are the limits here? With this kind of control at the nanoscale, what completely new types of materials could we design? Imagine combining different metals in these intricate shapes, what unique properties might emerge? And what other metal combinations or even more complex starting shapes could you tackle with this gentle approach? It feels like we're just starting to explore what's possible here.